So in this last section of this lesson, I want to say a few words about linear regression. It's a very easy form of regression, but we see it quite commonly. Now with the t-test and ANOVA, we were comparing the means of two or more groups, but those groups were categorical groups. The variable was categorical: white cell count, or temperature, or systolic blood pressure, or the value of some blood test. That name, that's categorical. But what if I wanted to compare numerical value to numerical value? So a set of values, set of numerical continuous data type values, I want to compare them. So in essence, I want to know, is there a correlation between two sets of numbers? Examples that I've listed there for the t-test and the ANOVA really is drug A and placebo, or patients in group A and patients in group B. Here we really want to do something else. We want an X value and a Y value, and we want to compare whether they are correlated to each other. Now these data points, as I've mentioned, they come in a pair, an independent and a dependent set of values. Now it's sometimes difficult to know which is the dependent and which is the independent. Example that's used in most statistical textbooks is just the outcomes of hours of study. So we'll look at students and what their test results were and look at how many hours they studied. So the independent variable would be number of hours studied, and depending on that, there's the dependent variable, that is the test score. So when it comes to the medical literature, you really have to see which one is which variable depends on which other one, which is the dependent and which is the independent variable. Now, as I mentioned, we will have these pairs of values, and we want to know, is there a correlation between them? Now, it turns out we can test the strength of that correlation, how one depends on the other, and we can also test for the direction of that dependence. Have a look at this. First of all, we're going to look at a positive correlation. Now, look at those set of values. You can well imagine the independent variable on the x-axis, and as that increases, the dependent variable on the y-axis changes accordingly. As the x values get larger, so the y values get larger. You can well imagine there's a single line you can draw through that. That is the actual correlation, the mathematics that happens behind the statistics. You can draw a line there that will show you, as the independent variable on the x-axis increases, so does the dependent variable on the y-axis. We can also have negative correlation. That's where we'll see this kind of pattern. As the independent variable increases, the dependent variable decreases. That would be a negative form of correlation. And then obviously we get no correlation whatsoever. As the one increases, the other one jumps around unpredictably. There is no pattern to this type of correlation. Now the strength and the direction, the mathematics, your computer, whatever you use to do that, calculates what is called the correlation coefficient, which is usually named an underscore R. Now that R takes a value from -1 all the way to +1 in decimal values. -1 being absolute negative correlation. Step by step, as the independent variable increases, the dependent variable decreases, step for step in a straight line. Perfect, perfect, perfect. +1, obviously positive correlation. As the independent variable increases, step by step, so does the dependent variable. And if you have an R value of 0, that's the last picture we saw. There's no correlation whatsoever. So that is linear regression.